In this lesson, we're going to be looking at vectors as they relate to velocity. Now, velocity is a term and a concept that we've looked at before. And as we discussed in the previous lesson, we looked at forces. We have velocities also have a magnitude and direction, so it's appropriate to represent them as a vector. Now, just as we've been doing with other vectors, quite often we're going to be combining vectors in some way to produce a resultant vector. In the case of velocity vectors, this isn't always appropriate, but there are a number of scenarios where it is appropriate. And a couple of simple examples to relate to would be, for example, a boat in a current. So if a boat is in a river, there's the velocity that the boat itself can generate, and there's also the velocity of the water in the river. A plane flying on a windy day, there's the velocity that the plane itself can generate, but there's also the velocity of the wind. And those different situations, the velocities will combine to give you a resultant velocity. When you're working on problems like this, a couple of things for you to keep in mind that will help you be more successful. As always, a neat diagram is always a good idea, showing how the vectors relate to each other. And then, if necessary, continue your diagram to show any kind of resultant velocity that you're looking for. And the other thing to keep in mind is know whether or not you're looking for the resultant vector, the velocity vector, or you might be given the resultant vector and you're being asked to find information about how you got there. So we'll do examples covering each of those two scenarios. So the first one, we've got a plane heading north with an airspeed of 400 kilometers per hour. It is blown off course by a wind of 100 kilometers per hour from the northeast. Now, when we talk about wind direction, it's a place where students quite often find it to be confusing because, to be honest, it actually is confusing. The conventions for describing wind speed are counterintuitive. So, on an upcoming page, I'm going to talk a bit about that. In this case, I chose this example. I tried to make it as clear as possible, underlining from. So this wind is coming from the northeast. Now, since we're dealing with compass directions here, the first thing we might want to make sure that we remind ourselves of is the north, south, east, and west for directions. And then I'm going to actually create a larger grid or a larger set of axes, and I'm going to draw in what I have so far. I could have done this all in one. So I have a plane heading north with an airspeed of 400 kilometers per hour. So that gives me the velocity of the plane, and that's going to be 400 kilometers per hour. And then it's being blown off course by a wind of 100 kilometers per hour from the northeast. From the northeast means that this wind is actually blowing to the southwest. Now, right now I've arranged so this is the velocity of the wind. The way I've arranged this right now, they're tail to tail. But in order to do a proper vector addition, I need to go tip to tail. Now, one of the properties of vectors we've talked about is that you can actually translate a vector wherever you like. It doesn't change the properties of the vector. So I could take this vector and actually put it here. And the reason for doing that is because that now allows me to perform my vector addition. That's a pretty poor. And so that's going to be my resultant vector. And that resultant vector, in this case, my resultant vector, is also referred to as the ground velocity. And I can't spell ground. So the resultant vector is the same as the ground velocity. So whether you use VR or whether you use VG, that's up to you. I started with VR, so I'll stick with that for now. So what we have here is actually just a simple triangle. So I'm going to draw yet another diagram. You don't have to go through all of these different layers of diagrams. So we have 400 which is the speed of the plane itself as given. We have 100, which is the speed of the air. And then over here we have what we're trying to solve for. And so I'm just going to write this as the absolute value of V sub r. That's that third side. Now, what other information do we have? We're told that it comes from the northeast. And that means directly northeast. And so that actually tells us that these two angles are 45 degrees. Northeast is exactly halfway between north and east. So northeast would be here, which would be 45 degrees here and 45 degrees here. But the wind itself is blowing then to the southwest. So we get 45 and 45. That can be translated. If we look, we've got an angle of 45 between the vertical and the vector VW. Between the vertical and the vector VW. So that angle is also 45 degrees. So that's equal to this angle. And that means that in this corner of our triangle, we have 45 degrees. So at this point, using triangle methods, we are now ready to find the magnitude of the resultant vector. So the magnitude of V sub r, and I have the angle across, so I have a side angle side situation. So this is going to be cosine law. The magnitude of V sub r squared is going to be 100 squared plus 400 squared minus 2 times 100 times 400 times the cosine of the angle across, which is the cosine of 45 degrees. If we do our calculations there, we find out that the magnitude of V sub r squared is equal to, works out to be, keeping in mind, just to remind you, we've got the cosine of 45 degrees. And so that's our 1 root 2 triangle. So this is 1 over root 2. So when we put all of this together, we end up with 170,000 minus 80,000 times 1 over root 2. And I'm going to need to take the positive square root of this to find my value for the resultant vector. So that's going to be an approximation, and I end up with 336.8. Now remember to keep all of those digits in your calculator if possible, or you're going to keep extra digits written out so that you can do your calculation to the greatest level of precision. Now the other thing I want to do is I want to describe, it's not good enough just to have the magnitude of this, I need to also describe some sort of direction. And in this case, it makes sense to describe the direction in terms of compass directions. So I'm going to want an angle between the vertical, and so I'm either going to want this angle or this angle. I want one of those two angles. In general, when we're describing compass directions, we want to describe a compass direction with an angle that's less than 45 degrees. But I don't know whether I'm going to get an angle, which one of these is going to be the smaller angle. But I do know that in my triangle here, that is certainly more convenient than trying to figure out this one. So I'm going to go ahead and label theta there. And just remember that this is to the vertical, this 400 is to the vertical. And so to find theta, I can make use of, I don't have angles, I can't add them up, so it looks like I can use either sine law or cosine law to find theta. Now if you use sine law to find theta, just be aware that if you use sine law to find theta, you need to then consider the redundant case that may come up here. We've got the ambiguous case for sine law. So I think I'll go ahead and show you in this case because I know this one's going to work out okay, and it's a good illustration of how to use sine law in this case. So I'm actually going to say that sine of theta over the sine of 45 degrees is equal to, and that's going to be across from theta is 100. Actually, let me that's not the way we normally write sine law to start. What I was going to write was correct, but it's not how we normally write sine law. We normally write sine law as sine A over A equals sine B over B equals sine C over C. So I'm going to say sine theta over 100 is equal to sine of 45 degrees over the magnitude of our resultant vector. And so from there I end up with sine theta is equal to 100 times the sine of 45, which is 1 over root 2 or root 2 over 2, over the magnitude of our resultant vector. Notice I'm just leaving this symbol in place as it is because I'm going to use the number that I've still got in my calculator to do this. And so I'm going to go ahead and do that all in one step. I end up taking the inverse sine of this whole calculation, and it works out to be approximately 12.1 degrees. But remember, we have ambiguous case, or we have to consider 180 degrees minus 12.1 degrees, which works out to be 167.9 degrees, and that's approximate as well. Now I said in this case, the ambiguous case is going to be easy to resolve, and that's true because 167.9 degrees, and we already know we have 45 degrees in the triangle, so we could say something like, but 167.9 degrees plus 45 degrees is greater than 180 degrees, which is not possible. Or it's actually not possible in a triangle. And so that means I reject this answer, and this has to be my answer. And as you can see, 12.1 degrees is an angle less than 45 degrees. So I'm now ready to describe that. And just to remind you, take a look at our diagram here. 12.1 degrees was this angle. 12.1 degrees. And so how would we describe that? That is north 12.1 degrees west. So therefore my ground velocity is, and we ended up with, what was our approximation for the magnitude? 336.8. 336.8 kilometers per hour, and my angle is 12.1 degrees. No, sorry, I didn't write that quite right. The angle is north 12.1 degrees west. Now, some terminology. If you are working on questions like this, you're going to see things like, for example, airspeed. When we talk about the airspeed of a plane, that's how fast a plane or any other flying object, that's how fast that object can actually travel in air if the air was still. One way to think about that would be the speed if it was a perfectly still day, or the speed under test conditions. That's the speed that the engines can generate. There's no term that we use for water, but it's the same idea. We imagine the speed in still water. When I talk about boats or canoes, I say, well, what if you were in a swimming pool where there's no current? That's the equivalent to airspeed. Ground speed, on the other hand, is how fast you're traveling on the or with respect to the surface of the Earth. And that means we also are taking into account any other effects. For example, the speed of the wind or the speed of the current or whatever else might be interfering with the air speed or the air travel of the object. When we talk about wind directions, and this is where I said things get counterintuitive, a west wind or westerly wind, for example, is a wind that's actually blowing towards the east. So a west wind or westerly wind means it's coming out of the west or from the west. I will generally try to use this language, but you may run into questions that refer to it this way. I will give you very explicit instructions on where the wind or the current is flowing to or where it's flowing from. And finally, speaking of flowing, you'll also see the words upstream and downstream. So if we focus on upstream, because downstream just means the opposite, upstream means to go against the current. And similarly, upwind means to go against the wind. Now, it doesn't mean we're necessarily going directly against the wind. So for example, if I have a river and the current is flowing that way, if I orient my boat to go this way, part of my boat's velocity is going across the river, but part of my boat's, if I break this into components, part of my boat's velocity is going directly across the river, and that has nothing to do with the current, but part of my boat's velocity is opposing the current. That would be an example of upstream. Downstream is the opposite. That's where part of your velocity is going along with the current. And it has to be one or the other. The only other option you have, of course, is you could go directly across, which means you're not directing your boat upstream or downstream, but you will always be pushed downstream. So let's take a look at another example. In this case, we are looking at water and a river. We have a river that's 2 kilometers wide, and the river itself flows at 6 kilometers per hour. So I'm going to orient my river vertically, and the river itself flows at 6 kilometers per hour. So this is the velocity of the current flowing down. You can, if you prefer, there's nothing wrong if you want to do something like this, north, south, east, west. That's up to you, but it's not really necessary in this case. We have a motorboat which can travel 20 kilometers per hour in still water. So that would be if it was in a swimming pool. No, that's what the motor is capable of generating, 20 kilometers per hour. And that person in the boat wants to reach the opposite shore directly across the river. So they want to start here and they want to travel. Essentially, they want to travel at a right angle and they want to arrive at a right angle. So how should the boat do this? How should they steer the boat in order to accomplish this? Well, if you think about starting here on the river, or actually at any point on the river, what's going to be happening is, first of all, let's imagine the boat has reached this part of the river. The current is going to be pushing the boat down the river, downstream. But I want my resultant to be across the river. So there is my velocity of my current. I know I want my resultant to be here across the river. So actually what I'm interested in is the velocity of the boat. Now I know the magnitude of that. I already know that the magnitude of the velocity of the boat is equal to 20 because that's given right there. So we actually know the length of this side. We know the length of this one. We don't actually know anything about the resultant except for its direction, which is directly across the river. So what we're interested in is how should the boat be steered? And what that's actually asking is an angle. So at what angle should I steer the boat? Now, traditionally, when we talk about steering a boat, we normally talk about the angle looking straight across from the river. So if this is the bank of the river, normally what we talk about, if I put in a right-angled perpendicular, when we talk about steering the boat, we're interested in this angle. So that's what we're interested in finding in this question. We're interested in finding the angle with respect to, as I've drawn it here, with respect to the horizontal. So to do that, let's go ahead and take a look at our triangle. So we have the resultant velocity, we have the current, we have the velocity of the boat in still water. And if we are interested in this angle, theta, that would be the same as this angle down here And because these are parallel lines, that's the same as this angle inside the triangle. And this is a right angle. And so from here, to find this angle, it turns out we don't actually need to know the size of the resultant velocity. We can find it easily enough. This is a right angle triangle, so the Pythagorean theorem would apply here. But we're interested in theta. How should the boat be steered? So we can use right angle trigonometry to say opposite and hypotenuse. So we can actually say the sine of theta is equal to the magnitude of the speed of the current over the magnitude of the speed of the boat, or the velocity of the boat, which is equal to, and since they're magnitudes, that's positive 6 over positive 20, that's sine of theta. And so from that we end up with theta is approximately equal to, and we end up with a value of 17.5 degrees. I'm just going to double check that. The inverse sine of 6 over 20 is equal to 17.5 degrees. And that would be, and the reason why we say this is that would be upstream. We're opposing. So therefore, we have to steer the boat 17.5 degrees upstream. Notice I didn't actually have to make a reference to the resultant velocity because that wasn't what the question was asking, at least not this time. And that's it for this lesson. So there's some homework that relates to velocity vectors.